We are going to fly today. We are going to basically do most of carbohydrates today. We'll do lipids next time and on Monday. We won't get to all of the lipids chapter. The exam will still be held as scheduled on Tuesday and Wednesday, but I will adjust what's on the exam to make sure we've covered it by the time we get there. All right, so chapter 24 is basically all about the structure of carbohydrates. And as I mentioned last time, some of this is going to be a review because we've dealt with hemiacetals before, and you've answered questions about carbohydrates before on your exams. Probably some of you even in 351, though you may not have known it. So I'm going to try to be really clear, and the study guide is really clear on what you need to know. You're going to need to know / memorize some things about structures of carbohydrates. What I've drawn for you is the cyclic hemiacetal form of glucose. But when we talk about carbohydrates, we have some nomenclature that you're going to need to learn. So we could write cyclic hemiacetal form of glucose. By the way, you have answered questions before on an exam about, I think you have anyway, which of the following is the open chain form of the molecule shown. To draw the open chain form of glucose, you simply identify carbon 1, which is the one that's the hemiacetal, and you can sort of count from there. Carbon 1 becomes an aldehyde, and everything else stays unchanged. Now I'm still drawing this from the sort of sideways perspective and converting that into something that's sort of linear with dashes and wedges is something that you've done before and that I won't spend any time on today. You've just got to make sure you get the stereochemistry right. The cyclic hemiacetal, so the open chain form is called simply D-glucose. The hemiacetal form has a more complicated name than just the cyclic hemiacetal form of glucose. It is beta D-glucopyranose. So the ose tells you that it's a sugar. The pyran part tells you specifically that it is a 6-membered ring. I'm not sure why. 6-membered ring with an oxygen. We'll see that some sugars like fructose later on, we won't do fructose in this chapter, but we'll get to it when we talk about metabolism. We'll see fructose is a furanose, that is a 5-membered ring, has a 5-membered ring cyclic hemiacetal form. The beta tells you about stereochemistry at carbon 1. Okay? When we draw glucose like this and the OH at carbon 1 is up, we call that beta. If the OH were down, we would call that alpha. So we can draw an alternative form of glucose in which the OH at carbon 1 is down, but everything else is in the same position. We call this alpha D-glucopyranose. What's the stereochemical relationship between alpha and beta D-glucopyranose? Diastereomers. There's that favorite word that we use for every kind of stereoisomer that is not an enantiomer. So alpha and beta D-glucopyranose differ in the location and in the configuration of one and only one stereocenter. So yeah, they are in particular often called diastereomers. We have another term for diastereomers that differ at one and only one stereocenter. That's called epimers. So they differ in configuration at only one stereocenter. And then we have another word besides epimers that we use for diastereomers that differ at the hemiacetal carbon. So to talk about this, I need to introduce a new term that you might have heard before. The hemiacetal carbon is often called the anomeric carbon. I'm not sure where that name comes from. But when you hear anomeric carbon, you need to think the carbon that's the hemiacetal or the carbon that's bonded to two oxygens. Okay, so the other term we have for these epimers of glucose is they are anomers of each other because they differ in configuration at the anomeric carbon. You'll hear people talk about glucose, alpha and beta forms of glucose. They'll call this is the alpha anomer, this is the beta anomer, or they could also say this is the alpha epimer, this is the beta epimer. They might also say this is the alpha diastereomer, this is the beta diastereomer. Okay? So questions about alpha and beta there? Okay, let's now talk about what the D refers to. I'll highlight that in orange. The D refers to stereochemical configuration at C5. Okay, that's the last stereocenter in the sugar. And when we draw glucose in this cyclic hemiacetal form, when C5 is up, we say it has D configuration. That is an old way of talking about stereochemistry. It's the D and L system. It's not based on any absolute configuration. It's related, it's stereochemical configuration assigned by analogy to a smaller related compound. It made sense 100 years ago. It no longer makes sense, but we continue to use the term. We used that same L and D stereochemical notation when we were talking about amino acids. I said all the 20 amino acids have the L configuration of the alpha carbon. It's a similar way of talking about stereochemistry for sugars. So most of the carbohydrates that are involved in biology, not all of them, but most of them have the D configuration at this particular carbon. Okay? So that's where the D comes in. Notice that the alpha and beta anomers of glucose both have the same configuration at C5. They are both D sugars. All right, and then finally, the gluco, what does that mean? Gluco refers to stereochemistry at C2, C3, and C4. So when we draw glucose in its cyclic hemiacetal form, carbons 2, 3, and 4 all have equatorial OH groups, and so we call it glucose. I don't know why. That's just the pattern of stereocenters that we use for glucose. It's easiest to memorize carbohydrates by memorizing the structure of beta-D-glucopyranose, and then you let the name tell you what to do for all the other carbohydrates. If you draw alpha, you know I switch stereochemistry at C1, the anomeric carbon. Okay, questions about that? There are two other carbohydrates whose structures I want you to know, and they are epimers of glucose. So the first is what I will call the C2 epimer of glucose, and that is D, we'll call it the C2 epimer of D-glucose. It's D-mannose. And I'm going to draw it here in its cyclic hemiacetal form, and its name is beta D mannopyranose. So you start out with the chair, and you're going to keep everything exactly the same as it is in glucose, only at C2, where instead of the OH group being equatorial down, it's now going to be axial up. And of course, this bond between carbons 4 and 5 is behind the up axial OH group. So that's beta D mannopyranose. And we call it, again, mano indicates that it's the C2 epimer of glucose. Don't like where that D is. Okay, so that's one to know. The reason I want you to know it is because it's found a lot in carbohydrate structures in nature. Okay, so if you memorize beta D glucopyranose, mannose is easy. You just switch the stereochemistry at C2. Okay. The next one is galactose, which is the C4 epimer of D-glucose. It's named from the Greek word for milk, same thing as the name galaxy, which sort of refers to the Milky Way. Galactose is a component of the sugar lactose that's found in milk and dairy. I will draw for you beta D galactopyranose, which you're going to start out again exactly the same as beta D glucopyranose, only we're going to switch the stereochemical configuration at C4. So whereas in beta D glucopyranose, C4 was down equatorial, now it's going to be up axial. And again, the galacto tells you that it's the C4 epimer of glucose. All right, so those are the three. Some of you may be wondering, is there a C3 epimer of glucose? Yes, there is. It's called allose, but it's not found a lot in biology, so it's not worth knowing unless you're a carbohydrate chemist, in which case you might want to know about it. But other than that, it's not really that useful to know. Yeah?
So at the beginning of the study guide for chapter 24, there was like a very brief mention of like 5-membered rings. Is there anything in particular that we should know about 5-membered?
5-membered ring carbohydrates. There are some sugars for which that is the predominant form. Fructose is one of them. If you look at the open chain form of D-glucose, you make a 6-membered ring by connecting the aldehyde on carbon 1 with the OH that's on carbon 5. If you wanted to make a 5-membered ring, you would need to use the OH that's on carbon 4. That is an option. It is known. You can make it in the lab. It's less stable than the 6-membered ring, though. So in terms of biology, that's not the form that's generally found for glucose. Yep. Others? Okay. Couple of things that this isn't necessarily anything I'm going to ask you about, but it's something I anticipate you will encounter perhaps even already in other classes where you learn about carbohydrates. Some people who are not you are uncomfortable drawing the chair. It makes them feel sad somehow, and so they prefer simpler options. So I'm going to show you briefly some other options for drawing carbohydrates. One of them is, I'm going to get this wrong. I always write it down wrong, but I don't care. The Haworth projection. There may be O's in there instead of A's. I'm not sure. To do this, you simply take the the closed chain form of glucose in its chair, and number 1, 2, 3, 4, 5, and 6. Then you're going to draw a hexagon on its side, sort of a squat hexagon, sort of leaning. So we're sort of taking a side view of a 6-membered ring. And then you're gonna lose the concept of the chair, and you're gonna simply go up and down for the various groups on the ring. So I'm gonna number again around the ring. 1, 2, 3, 4, 5. On carbon 1 in beta D glucopyranose, the OH group is up. So I'm going to draw a straight vertical line. Do not tell me that that does not accurately portray an sp3 hybridized carbon, because I already know. But the people that like this don't care. Carbon 2, glucose, the OH group is down. So you're going to draw a line straight down. You can include or not the hydrogens. I haven't included I included them on we'll do it here just to be consistent. On carbon 3, the OH group is up. So, oops, I erased too much. So that would be vertical up, and then hydrogen is down. On carbon 4, the OH is down, so we'll draw it vertically down. And then on carbon 5, the CH2OH, that's carbon 6, will be up, and then the hydrogen would be down. I don't like how I've drawn that, so I'm going to omit the hydrogen on carbon 5, but you can envision it there. So that's one common way to draw carbohydrates. Now, you don't want to know this, but there is an alternative way to draw carbohydrates as well. It's called the Fisher projection, and the Fisher projection is for the open chain form of carbohydrates. It is not so bad to use if you know what it means. If you don't know what it means, it looks like scratches on paper, and you totally lose the concept of stereochemistry. Your text will take you through it. If you want to know more, I'm going to simply refer you back to it, because I promise not to ask you questions on my exams about Fisher projections. However, they're really easy to write exam questions about Fisher projections on the MCAT or the DAT or other standardized exams that you might take. There's probably a 50-50 shot of you encountering it in biochem. So I'm going to take just a minute and show you how to convert. I've already showed you how to convert from the chair conformation, which is the most physically realistic, to the less physically realistic but still cyclic Haworth projection. And I'm going to show you how to convert the Haworth projection into the Fisher projection. So should you need to use it, you can. It's pretty simple. All you do is you start with the Haworth projection, and you convert it into its open chain form. Now notice the hemiacetal carbon here. This is the carbon that's going to be the aldehyde, and this will simply be the OH group on carbon 5. Okay, so I'm going to make this an OH group. I'm going to erase the stuff on carbon 1, and I'm just going to make carbon 1 an aldehyde, which is referred to as CHO, which is the abbreviation that organic chemists use for an aldehyde. Okay, got it so far? CHO, yeah. Then we are going to, I'm going to draw the hydrogen on carbon 5 so that we can see it. Then we're going to conceptually unravel some stuff. First, we need to do something about carbon 5, because in the Fisher projection, we want a linear chain going from carbon 1 to 2 to 3 to 4 to 5 and then to 6. So we need to actually rotate around the bond between carbon 4 and 5 to trade the positions, swing CH2OH down into that position. If we do that, that's going to swing this CH2OH here, it's going to move this OH here, and it's going to move the hydrogen up. We're just rotating around a carbon-carbon bond. You might need a model to see you how to help you see how to do this. After I rotate around that carbon-carbon bond, what I will have after that looks like this. As I said, don't stress out about this if you can't do it. You won't need to for me, but I'm preparing you for the future in case you should have to do this then. OH here, hydrogen here, OH here, CHO here. Carbon 1, 2, 3, 4, 5, and 6. Then what we're going to do is simply unravel the carbon chain. We're going to swing carbon 1 down to be a straight line from carbon 2. We'll swing carbon 4 down to be a straight line from carbon 3. We'll swing 5 around and 6 around so that we have something that's like this. CHO on this end, 1. Carbon 2 with an OH here and a hydrogen here. Carbon 3 with an OH here and a hydrogen here. Carbon 4 with an OH down and a hydrogen up. Carbon 5 with an OH up. Wait, I did that wrong, didn't I? There's muttering in the audience. I can always tell when I've done something wrong when there's muttering in the audience. You guys should speak up sooner. You are right, the OH, if we rotate around the bond like I showed you. Did I do it wrong again? Yeah. Thank you. See, you spoke up sooner. Doesn't that feel good? Come on, speak truth to power. All right. Are we better on carbon 5? Are we all in agreement there? Basically. That's carbon 6. Okay. That's the Fisher projection, only it's traditional to rotate it up like this. Put carbon 1 at the top, carbon 6 at the bottom, and then use lines for carbons 2, 3, 4, 5, and 6. Whoa. And then we simply keep, since we've rotated it up kind of counterclockwise, everything that was down is on our right, and everything that was up is on our left. So that's the Fisher projection for D-glucose. If you want to know more about what this means from a stereochemical point of view, we'll just zoom in on one carbon 1, CHO, OH, H, and then we'll call this R. What this actually means, it's a really weird way of looking at a stereocenter. It's sort of looking at it on the edge. The OH and the hydrogen are pointing out towards you as wedges, and the CHO and the R group are pointing away from you as dashes. So some people try to start with this, put all the stereocenters in like this, and then watch their brains explode as they try to twist that around into something that an organic chemist could look at and say that's a reasonable looking structure. I find it's easiest to start from the chair and go there. Or alternatively, you can memorize this as the structure of D-glucose, and then because you know mannose is the C2 epimer and galactose is the C4 epimer, you just switch the configuration of the OH and then it's easy. Okay? All right, as I said, promise not to ask you about Fisher projections, but I can pretty much guarantee you'll see it in your future. So you can come back to these notes and deal with that at some point. Okay. Now we need to talk, there is so much more we could say about carbohydrates. One of the things I didn't say was that the alpha and the beta anomers are in equilibrium with each other. Okay? I showed you that the beta anomer is in equilibrium with the open chain form of D-glucose. So we'll sort of draw that here. And that's simply opening of a cyclic hemiacetal. It turns out that the alpha anomer is also in equilibrium with the open chain form. And whether you get the alpha or the beta anomer really depends on rotation around the bond between carbons 1 and 2 when you go to make the cyclic hemiacetal, right? If this oxygen attacked this carbon here in this shape, we'd get the beta anomer. However, if we had rotated around this bond so that the oxygen and the aldehyde were here and the hydrogen were here, we'd get the alpha anomer. So that's one way that alpha and beta anomers can interconvert, is through the open chain form. But there's another way they can interconvert. There's another pathway, and that's through an oxonium ion that looks like this. Okay, let's talk through this conceptually, see if we need to actually draw the mechanism or not. How would I get from this open chain form to this oxonium ion? Any ideas? This is like a mechanism question on a previous exam, right? If I want neutral oxygen to kick off negatively charged OH group, is that a smart choice? No. What do I need to do first? Protonate. So yeah, we would have H3O plus, the minimal amount that's in water. This can happen in neutral water. Protonate this, turn it into the hydronium sort of group, right? Then, once that had happened, electrons could kick down and kick off water as a leaving group, right? That would get you to the oxonium ion. I'm going to just keep things drawn like that. How would I get from the oxonium ion to the alpha anomer? Where would OH need to attack? From below, right? If it attacks from above, I get this stereochemistry right back to the beta anomer. If I want to get to the alpha anomer, I would show water attacking from below in the same way that you'd show attacking a carbonyl. That would lead me to this intermediate, and then water would remove the proton from that group to give me the alpha anomer. Yeah?
Is it one or two steps for the OH leaving and then the oxygen electrons? Like, does the oxygen kick off the OH, or does the OH leave making it?
I see. Yeah, I see what the question is. So you'll see this done in a couple of different ways, and it turns out they're equivalent. The question is, once that OH on carbon 1 is protonated, does it leave to give something that looks like this, with a positive charge on carbon 1? Or does it do what I showed you, which is electrons on the oxygen kick down to kick the group off? I assert that those two options are entirely equivalent. Why? Because those two products that you're seeing as different are actually not different products. They're resonance structures of each other. Do you see how the only difference between this and this is the electrons on the oxygen? Those are resonance structures. So you can show you can show this going to the oxonium ion in two different equivalent ways. You can show the OH, the water leaving group leaving, and it looks kind of like an SN1 style reaction, and that would get you to this resonance structure of the oxonium ion, or alternatively, you can show these electrons kicking down and the leaving group leaves to get to that resonance structure. Identical ways of thinking about it. Good. Others? Yeah. Say that a little bit louder, sorry. Do we ever do stuff with the alpha carbon in the open chain form? Right, in the open chain form, we're alpha to a carbonyl. That's a potentially acidic position. Yes, when we get to metabolism of glucose, we will see that one of the things that happens involves making the enolate there, or actually tautomerizing to the enol. Yep, saw another hand. Did I miss you out here? No takers. Okay, great. So that process of converting really through either of these methods from the alpha to the beta anomers, this is a term that only organic chemists care about. I'm not sure whether I will say it ever again or not, but it just is occurring to me, so I'll say it. It's called mutarotation. Muta because it's not actual rotation around bonds. It involves chemical reaction, but it looks like you've just popped the OH group off and put it back in a new location. And equilibrating between alpha and beta forms can happen via either of these ways. Now, if we had infinite time, I would tell you a lovely story about which of these two you'd expect to be more stable. By the way, which is it, based on what you know about chairs? Better to have it axial or equatorial? Equatorial, yes. However, and I don't know if you remember something from 351 about A values, you can tell just how bad it is to have something axial versus equatorial. And you could calculate a theoretical ratio of alpha and beta anomers based on that. You would have predicted more of the beta anomer than the alpha anomer. It turns out that you see more of the alpha anomer than would be expected, just based on sterics alone, which means there's something interesting going on here that I don't have time to tell you about. If you want to know more about it, come talk to me sometime. It's kind of a fun story. It involves something called hyperconjugation, which is a fun topic, but which we're not talking about in a lot of detail. Okay, we need to spend the last few minutes today talking about more complicated carbohydrate structures. And this is where you can convert glucose and galactose and mannose hemiacetals into what are called glycosides, which are just acetals. So let me introduce to you the simplest glycoside I could think of. This is an acetal form of a carbohydrate. So imagine that you have here beta-D-glucopyranose. By the way, sometimes it is difficult. Actually, in aqueous solution, glucose exists in its pyranose form, but in a mixture of alpha and beta anomers. When you want to communicate that you have a mixture of alpha and beta anomers, one thing that organic chemists do is use a squiggly line for the C1OH group. That says we are not committing to whether it's up or down. We have both. Okay? So that squiggly line simply means I've got both alpha and beta anomers. Suppose I added an acid catalyst and an alcohol. I'm not going to be very specific about the acid catalyst I might add. If you wanted to make me pick an organic soluble acid like toluene sulfonic acid, not under aqueous conditions, would be a good choice. You can, at that point, convert from the hemiacetal into the acetal at the anomeric carbon, where the OH will be lost as water and replaced by the alcohol oxygen. And you could call this an acetal, and it is. It is also called a glycoside, which means an acetal using the anomeric carbon of a carbohydrate. And you might also call it a methyl glycoside because the alcohol was methanol. Okay? Now, how do we get this? How does it happen? It's actually quite simple. You're going to first protonate, First protonate the oxygen with your acid. This is exactly the same as how we interconvert alpha and beta anomers in the first place. So now the OH is a good leaving group. Feel free to abbreviate the rest of the glucose molecule if you want to. Then the lone pairs on the oxygen can kick down and make the leaving group leave. That will get you to this oxonium ion, which we drew before in the mutarotation process. Now that we've got that oxonium ion, methanol can act as the nucleophile, and it can attack that carbonyl carbon either from above or below. And that's going to make the new carbon-oxygen bond. I will continue to use a squiggly line to indicate that we have a mixture of alpha and beta configuration at C1. And then in the final step, we'll use the conjugate base of our acid or perhaps another molecule of methanol to remove the proton, and that will get us to the glycoside product. Okay, so that's forming an acetal. That's the basic mechanism. Now, if you are troubled by this, it could mean that you need to review acetal formation, but you might be troubled by it for other reasons. One of the reasons you could be troubled by it is you noticed that the alcohol is the nucleophile here, but we have tons of alcohols in the sugar itself. So you might be wondering, why doesn't one of those alcohols reach over and attack? And the answer is ring strain. But you could ask, why doesn't an alcohol group on another sugar do the attacking to make the acetal? That actually does happen, and it's difficult to control. In fact, if you've ever made rock candy, one of the things you're doing as the temperature increases is you're forming glycosides. You're forming linkages between OH groups on one sugar and the anomeric carbon on the other. So I'm going to show you some of these glycosidic linkages in which it's not methanol being the nucleophile at this step, but an OH group from another sugar. If you want to do this in a controlled way in the lab, you've got to use protecting groups. And welcome to the research of my esteemed colleague, Dr. Paul Savage, who has an area in his group that's exclusively carbohydrate chemistry. And it's a lot of protecting group stuff to get the right OH group to do the right thing. Biology, you've got enzymes that take care of this. In your pot on the stove when you're making rock candy, it's totally uncontrolled, but you don't care because all you want it is to be a nice, deliciously sweet solid. And so you don't really care which OH group is bonded to which. So let me show you some simple glycosidic linkages from sugars that you may know about. These aren't things to memorize, but I do want you to be able to talk about the different linkages involved in these various sugars. So let's start out with dairy. So here's lactose. So lactose involves, on the left-hand side, a galactose unit. You can tell that this is galactose because, except I can't count, the OH group is up on carbon 4. In galactose, C1 is bonded to an oxygen, but that oxygen itself comes from C4 of a different carbohydrate unit. This will be glucose. I'm going to choose a mixture of alpha and beta anomers at the anomeric carbon because that's what it would be. In aqueous solution, you'd have a mixture of both. Okay, so this is lactose. You have you have the cyclic form of galactose on the left-hand side, and then you have the cyclic form of glucose on the right-hand side. So this is a disaccharide because it's got 2 carbohydrate units. We want to talk about this linkage between the 2 carbohydrate units. It's between carbon 1 on the one sugar and carbon 4 on the other sugar. And then what's the stereochemical configuration of carbon 1 on galactose? It's beta, right? It's up. So we're going to call this a beta 1,4 glycosidic linkage, meaning it is a linkage in between 2 carbohydrate units. The glycoside there in glycosidic tells you that this is an acetal. The anomeric carbon of the acetal is carbon 1, and it's got beta 1,4. So if I told you that lactose is the beta 1,4 connection of galactose on the left and glucose on the right, you could draw that structure unambiguously. Okay? Now, where does lactose intolerance come from? It turns out that human infants express an enzyme called beta-galactosidase that hydrolyzes this acetal. So you can break lactose down into galactose and glucose. For a lot of people, the intestines stop expressing that enzyme as you age, presumably because distant in our ancestry, we didn't get a lot of nutrition from dairy, and therefore there was no need for the enzyme. And so over time, humans tended to become what's called lactose intolerant, because they lack the enzyme to hydrolyze this linkage. Fortunately, you have intestinal and gut microbiome that can hydrolyze the linkage, but that often results in gas and bloating and unpleasant symptoms. My son, Jack, who's the Kentucky missionary, thinks he can train his intestines to overcome this by simply powering through. The ice cream is worth it or something. Anyway, it's an interesting story in human evolutionary history and sort of migration. If you have ancestors from Europe, thousands upon thousands of years ago, Europeans learned how to make cheese and preserve dairy products. And so there was now a selective advantage if you could comfortably get nutrition from dairy products. And so to this day, if you have European ancestry, you likely are not lactose intolerant. If you don't, you might be. And it just has to do with that enzyme. Of course, there are lovely products now where you can supplement with that enzyme and so on. Okay, there's more to talk about. So that's lactose. Let's look at maltose. So maltose is a disaccharide of glucose subunits. Only in maltose, the configuration of the anomeric carbon is alpha, and then the oxygen that is attached to that anomeric carbon is, again, C4 of another glucose unit. So we would call this an alpha 1,4 linkage of 2 glucose subunits. So if you get good at this, what I'll expect you to be able to do on an exam is look at a carbohydrate, perhaps even larger than this, and tell me, what is this subunit? Is that glucose, galactose, or mannose? And then also, what is that glycosidic linkage? Is it beta 1,4, alpha 1,4? Is it alpha 1,6, beta 1,6? A lot of different ways that you can, a lot of different glycosidic linkages you can envision. Okay, questions about that so far? Let's talk maybe about the difference between fiber and starch. So this is one I'm sure that you've probably learned in other settings. Plant cell walls have a major component of a glucose, a long extended polymer. I'm only showing you a 2-saccharide subunit of that polymer. What I'm drawing you here is called cellobiose, but it's a 2-carbohydrate polymer subunit of cellulose, which is basically plant cell wall. Again, you've got glucose subunits, which I'm abbreviating as GLC, and it's a beta 1,4 linkage. And that makes a big difference. We don't have enzymes that digest that linkage, so you can eat plant cell walls, but you don't gain nutrition from them. They help with your GI tract health, but you don't necessarily gain any specific nutrition from them. If we change the stereochemical configuration from beta to alpha, you now have maltose, right? Which you can digest, and which if you put in your mouth will taste sweet because your enzymes in your saliva are already hydrolyzing that alpha 1,4 linkage. If you look in your text, we don't have time to draw all of this for you right now, but you will see structures of amylose and amylopectin. Amylose is just a polymer of maltose units, one glucose after another, all with alpha 1,4 linkages. Amylopectin is where the C6OH group is occasionally linked to another glucose unit. So you get branch points, and you'll learn if you want to get into this when you start talking about glycogen, what are the linkages that are present in glycogen versus starch, and it all has to do with the stereochemistry of these connection points. So that's a bunch of stuff to memorize, but hopefully it illustrates one key principle that's been true even in the peptides and proteins and amino acids chapter, which is the relationship between structure and function. One stereocenter different use biologically, different structures, different conformations, different biological uses. Okay, let's see. Lastly, we need to talk about some versions of carbohydrates that have nitrogens in them. I still got 2 minutes. What are you complaining about? Okay, maybe less than 2 minutes. If you take glucose and you keep everything the same, but at C2 you put an NH2 group, this is called glucosamine. All right? And if you put an acetyl group on that NH2, it is called N-acetylglucosamine. Glucosamine you've probably heard of from what? You're supposed to, sometimes people take it for what? As a supplement for like joint health. Glucosamine is a carbohydrate that's a component of extracellular matrix, and so it's sometimes people use it for that purpose. N-acetylglucosamine is a carbohydrate that is found in chitin, which is insect shells. And so again, small structure changes lead to big differences in function and properties. You can make polymers of N-acetylglucosamine and you make something that's rigid like chitin. If you make polymers of cellobiose, you get something that's not quite as rigid. If you make polymers of maltose, you get something that you can eat. All right, that concludes our carbohydrates chapter. I will see you next time for lipids.